Good morning and hello everyone. Today we would like to present an applications of first order linear, which is dissolved sugar in a tea. This example helps us understand how substance dissolve in liquids and how the process happens in daily life. By using tea as an example, we can clearly see how sugar mix and spreads evenly in a liquid. Before that, let me introduce our team members. On the left side is me, Nur Alia Akila binti Zamri, and on the right side is my partner, Nur Fadila binti Muhammad Zain.
I'm going to talk about linear differential equations, or LDE. LDE is an equation that involves a function, its derivative, and the independent variable, usually x. It is called linear because the functions and its derivative only appear to the first power and are not multiplied together. The general form of first order LDE is dy over dx plus pxy equal to qx. Here, px and qx are functions of x, and y is the dependent variable. This form is important because it helps us identify whether an equation is linear or not. To solve a LDE, we usually use a method called integrating factor. The formula is e to the power of integrate px dx. After find the integrating factor, we multiply the whole equation by it. This allows the left side of the equation to be written as the derivative of the product. Then we integrate both sides to find the solution for y. Next is topic introduction. Mixture problems are about liquids flowing into and out of a tank. This causes the amount or concentration of a substance to change over time. We assume the liquid is always well mixed. Using differential equations, we can find how the concentration changes. These problems are useful in real-life situations like sugar in a tea. Dissolve sugar in a cup of a tea. A common example is sugar dissolving in a tea. If tea flows into a cup, while the same amount flows out and the mixture is well stirred, the sugar spreads evenly throughout the liquid. The amount of sugar changes continuously, and this process can be described mathematically using the first order LDE. By solving this equation, we can predict the sugar concentration in tea at any given time, demonstrating how mathematics can model everyday situations.
Now, let's move on to the problem statement. A cup contains 1 liter of tea with 20 grams of sugar. Tea with 5 grams per liter of sugar flows in at 0.1 liter per minute. The mixture flows out at the same rate. The solution is well stirred. Find the amount of sugar in the tea after t minutes. For this part, we are solving a mixing problem using a linear differential equation LDE. First, from the problem, we are given several important values. The initial amount of sugar in the tank is A0 equal to 20 grams. The inflow rate and outflow rate, which is R1 and R2, are both 0.1 liter per minute. The concentrations of sugar in the inflow is 5 grams per liter. This is actually C1. The volume of the solution is 1 liter and it is constant. Next, we form the differential equations. By substituting the given values, we will get dA per dt plus 0.18 equal to 0.5. This is a first order linear differential equation. To solve it, we use the integrating factor method, which is IF equal to e the power of integrate 0.1 dt. So the answer is e the power of 0.1t. We multiply both sides of the equation by this integrating factor, and it will be simplified to d over dt times a e the power of 0.1t equal to 0.5 e the power of 0.1t. This is actually an equivalent. Next, we integrate both sides with respect to t. After we integrate it, we will divide both sides by e the power of 0.1t. Then we will get the equations ap equal to 5 plus ce the power of negative 0.1t. Finally, we use the initial condition a0 equal to 20 to find the constant c. So it will be 20 equal to 5 plus c, and c is equal to 15. Therefore, the final solution is at equal to 5 plus 15e the power of negative 0.1t. This equation represents the amount of sugar in the tank at any time t. Now, let's move on to the second problem. You have a pot with 10 liters of plain tea. You start pouring in the tea containing 20 grams per liter of sugar at a rate of 2 liters per minute. The mixture leaks out of the bottom at 2 liters per minute. How much sugar is in the pot after 5 minutes? From the problem statement, we are given the following information. The volume of the tank is 10 liters. The inflow rate and outflow rate, which is R1 and R2, are both 2 liters per minute. The concentrations of sugar in the incoming solution is 20 grams per liter. The question asks how much sugar is in the tank after 5 minutes. Using the standard mixing model, substituting all the given values into the equations, we will get dA per dt plus 0.2a equal to 40. This is a first order linear differential equation, so we solve it using the integrating factor method. First, we find the integrating factor. IF equal to e the power of integrate 0.2 dt. So we will get the answer e the power of 0.2t. Next, we multiply both sides of the differential equation by e the power of 0.2t. Then we simplify it to d over dt times a e the power of 0.2t equal to 40 e the power of 0.2t. Now we integrate both sides with respect to t, and then we dividing both sides by e the power of 0.2t, and then we will obtain the equations of at equal to 200 plus c e the power of negative 0.2t. To find the constant c, we use the initial conditions at time t equal to 0, which is there is no sugar in the tank, so a0 equal to 0. Substituting this value, 0 equal to 200 plus c, so c is equal to negative 200. Therefore, these solutions becomes at equal to 200 minus 200 e the power of negative 0.2t. Finally, we evaluate the amount of sugar after 5 minutes. We replace t to 5, so it will be a5 equal to 200 minus 200 e the power of negative 0.2 times 5. So the final answer will be 126.4 grams. So after 5 minutes, the amount of sugar in the tank is approximately 126.4 grams.
In conclusion, mixture problems help us to understand how the amount of a substance changes when something is added and removed at the same time. In the sugar and the tea situation, the sugar content gradually changes and eventually reach a steady value because the incoming concentration and outgoing concentration balance each other. These problems show how real-life processes like mixing drinks, chemical solutions, or even medical IV fluids can be modeled and predicted using mathematics. This is our reference. Thank you.